Introduction. The Earth receives almost all of its energy from the Sun. The Earth in turn radiates back to space the energy received from the Sun. As a result, the Sun neither warms up nor does it get cooled over a period of time. Thus, the amount of heat received by different parts of the Earth is not the same. This variation causes pressure differences in the atmosphere. This leads to transfer of heat from one region to another by winds. Now let us know about the process of heating and cooling of the atmosphere and the resultant temperature distribution over the Earth's surface. Solar radiation. The Earth's surface receives most of its energy in short wavelengths. The energy received by the Earth is known as incoming solar radiation, which in short is termed as insolation. As the Earth is a gynoid resembling a sphere, the Sun's rays fall obliquely at the top of the atmosphere and the Earth intercepts a very small portion of the Sun's energy. On an average, the Earth receives 1.94 calories per square centimeter per minute at the top of its atmosphere. The solar output received at the top of the atmosphere varies slightly in a year due to the variations in the distance between the Earth and the Sun. During its revolution around the Sun, the Earth is farthest from the Sun, 152 million kilometers on 4th July. This position of the Earth is called aphelion. On 3rd January, the Earth is the nearest to the Sun, 147 million kilometers. This position is called perihelion. Therefore, the annual insolation received by the Earth on 3rd January is slightly more than that of the amount received on 4th July. However, the effect of this variation in the solar output is masked by other factors like the distribution of land and sea and the atmospheric circulation. Hence, this variation in the solar output does not have great effect on daily weather changes on the surface of the Earth. Variability of insolation at the surface of the Earth. The amount and the intensity of insolation vary during a day, in the season, and in a year. The factors that cause these variations in insolation are the rotation of the Earth on its axis, the angle of inclination of the Sun's rays, the length of the day, the transparency of the atmosphere, the configuration of land in terms of its aspect. The last two, however, have less influence. The fact that the Earth's axis makes an angle of 66.5 degrees with the plane of its orbit around the Sun has a greater influence on the amount of insolation received at different latitudes. The second factor that determines the amount of insolation received is the angle of inclination of the rays. This depends on the latitude of a place. The higher the latitude, the less is the angle they make with the surface of the Earth, resulting in slant sun rays. The area covered by vertical rays is always less than the slanting rays. If more area is covered, the energy gets distributed and the net energy received per unit area decreases. Moreover, the slant rays are required to pass through greater depth of the atmosphere, resulting in more absorption, scattering, and diffusion. The atmosphere is largely transparent to short-wave solar radiation. The incoming solar radiation passes through the atmosphere before striking the Earth's surface. Within the troposphere, water vapor, ozone, and other gases absorb much of the near-infrared radiation. Very small suspended particles in the troposphere scatter visible spectrum both to the space and towards the Earth's surface. This process adds color to the sky. The red color of the rising and the setting sun and the blue color of the sky are the result of scattering of light within the atmosphere. The insolation received at the surface varies from about 320 watt per meter square in the tropics to about 70 watt per meter square in the poles. Maximum insolation is received over the subtropical deserts where the cloudiness is the least. Equator receives comparatively less insolation than the tropics. Generally, at the same latitude, the insolation is more over the continent than over the oceans. In winter, the middle and higher latitudes receive less radiations than in summer. Heating and cooling of atmosphere. There are different ways of heating and cooling of atmosphere. The earth, after being heated by insolation, transmits the heat to the atmospheric layers near to the earth in long wave form. The air in contact with the land gets heated slowly, and the upper layers in contact with the lower layers also get heated. This process is called conduction. Conduction takes place when two bodies of unequal temperatures are in contact with one another. There is a flow of energy from the warmer to the cooler body. The transfer of heat continues until both the bodies attain the same temperature or contact is broken. Conduction is important in heating the lower layers of the atmosphere. The air in contact with the earth rises vertically on heating in the form of currents and further transmits the heat of the atmosphere. This process of vertical heating of the atmosphere is known as convection. The convective transfer of energy is confined only to the troposphere. The transfer of heat through horizontal movement of air is called advection. Horizontal movement of the air is relatively more important than the vertical movement. In middle latitudes, most of the diurnal day and night variation in daily weather are caused by advection alone. In tropical regions, particularly in northern India, during summer season, local winds called Lu is the outcome of advection process. Terrestrial radiation. The insolation received by the earth is in short waves forms and heats up its surface. The earth, after being heated itself, becomes a radiating body, and it radiates energy to the atmosphere in long wave form. This energy heats up the atmosphere from below. This process is known as terrestrial radiation. The longer wave radiation is absorbed by the atmospheric gases, particularly by carbon dioxide and other greenhouse gases. Thus, the atmosphere is indirectly heated by the Earth's radiation. The atmosphere in turn radiates and transmits heat to the space. Finally, the amount of heat received from the sun is returned to space, thereby maintaining constant temperature at the Earth's surface and in the atmosphere. Heat budget of the planet Earth. Figure depicts the heat budget of the planet Earth. The Earth as a whole does not accumulate or lose heat, it maintains its temperature. This can happen only if the amount of heat received in the form of insolation equals the amount lost by the Earth through terrestrial radiation. Consider that the insolation received at the top of the atmosphere is 100%. While passing through the atmosphere, some amount of energy is reflected, scattered, and absorbed. Only the remaining part reaches the Earth's surface. Roughly 35 units are reflected back to the space even before reaching the Earth's surface. Of these, 27 units are reflected back from the top of the clouds and 2 units from the snow and ice-covered areas of the Earth. The reflected amount of radiation is called the albedo of the Earth. The remaining 65 units are absorbed, 14 units within the atmosphere and 51 units by the Earth's surface. The Earth radiates back 51 units in the form of terrestrial radiation. Of these, 17 units are radiated to space directly, and remaining 34 units are absorbed by the atmosphere. 6 units absorbed directly by the atmosphere, 9 units through convection and turbulence, and 19 units through latent heat of condensation. "48 units absorbed by the atmosphere, 14 units from insolation, plus 34 units from terrestrial radiation are also radiated back into the space. Thus, the total radiation returning from the Earth and the atmosphere respectively is 17 plus 48, that is equal to 65 units, which balance the total of 65 units received from the Sun. This is termed the heat budget or heat balance of the Earth. This explains why the Earth neither warms up nor cools down despite the huge transfer of heat that takes place. Variation in the net heat budget at the Earth's surface. As explained earlier, there are variations in the amount of radiation received at the Earth's surface. Some part of the Earth has surplus radiation balance while the other part has deficit. There is a surplus of net radiation balance between 40 degrees north and south, and the regions near the poles have a deficit. The surplus heat energy from the tropics is redistributed polewards, and as a result the tropics do not get progressively heated up due to the accumulation of excess heat, or the heat latitudes get permanently frozen due to excess deficit. Temperature. The interaction of insolation with the atmosphere and the Earth's surface creates heat, which is measured in terms of temperature. While heat represents the molecular movement of particles comprising a substance, the temperature is the measurement in the degree of hot or cold a thing or a place is. Factors controlling temperature distribution are the latitude of the place, the altitude of the place, distance from the sea, the air mass circulation, the presence of warm and cold ocean currents, local aspects. Factors controlling temperature distribution are the latitude. The temperature of a place depends on the insolation received. It has been explained earlier that the insolation varies according to the latitude, hence the temperature also varies accordingly. The altitude. The atmosphere is indirectly heated by the terrestrial radiation from below. Therefore, the places near the sea level record higher temperature than the places situated at higher elevations. In other words, the temperature generally decreases with increasing height. The rate of decrease of temperature with height is termed as normal lapse rate. It is 6.5 degrees Celsius per 1000 meters. Distance from the sea. Another factor that influences the temperature is the location of a place with respect to the sea. Compared to land, the sea gets heated slowly and loses heat slowly. Land heats up and cools down quickly. Therefore, the variation in temperature over the sea is less compared to land. The places situated near the sea comes under the moderating influence of the sea and land breezes, which moderate the temperature. Air mass and ocean currents. Like the land and sea breezes, the passage of air masses also affects the temperature. The places which come under the influence of warm air masses experience higher temperature, and the places that come under the influence of cold air masses experience lower temperature. Similarly, the places located on the coast where the warm ocean currents flow direct higher temperature than the places located on the coast where the cold currents flow. Distribution of temperature. The global distribution of temperature can well be understood by studying the temperature distribution in January and July. The temperature distribution is generally shown on the map with the help of isotherms. The isotherms are lines joining places having equal temperature. In general, the effect of the latitude on temperature is well pronounced on the map as the isotherms are generally parallel to the latitude. The deviation from this general trend is more pronounced in January than in July, especially in the northern hemisphere. In northern hemisphere, the land surface area is much larger than in the southern hemisphere. Hence, the effects of landmass and the ocean currents are well pronounced. In January, the isotherms deviate to the north over the ocean and to the south over the continent. This can be seen on the North Atlantic Ocean. The presence of warm ocean currents, Gulf Stream and North Atlantic Drift make the Northern Atlantic Ocean warmer and the isotherms bend towards the north. Over the land, the temperature decreases sharply and the isotherms bend towards south in Europe. It is much pronounced in the Siberian plain. The mean January temperature along 60-degree equator longitude is minus 20 degrees Celsius both at 80-degree north and 50-degree north latitude. The mean monthly temperature for January is over 27 degrees Celsius in equatorial oceans, over 24 degrees Celsius in the tropics, and 2 degrees Celsius to 0 degrees Celsius in the middle latitudes and minus 18 degrees Celsius to minus 48 degrees Celsius in the Eurasian continental interior. The effect of the ocean is well pronounced in the southern hemisphere. Here, the isotherms are more or less parallel to the latitudes and the variation in temperature is more gradual than in the northern hemisphere. The isotherm of 20 degrees Celsius, 10 degrees Celsius and 0 degrees Celsius runs parallel to 35 degrees south, 45 degrees south and 60 degrees south latitudes respectively. In July, the isotherms generally run parallel to the latitude. The equatorial oceans record warmer temperature more than 27 degrees Celsius. Over the land, more than 30 degrees Celsius is noticed in the subtropical continental region of Asia along the 30-degree north latitude. Along the 40-degree north runs the isotherm of 10 degrees Celsius and along the 40-degree south the temperature is 10 degrees Celsius. The highest range of temperature is more than 60 degrees Celsius over the northeastern part of Eurasian continent. This is due to continentality. The least range of temperature, 3 degrees Celsius, is found between 20 degrees south and 15 degrees north. Inversion of temperature. Normally, temperature decreases with increase in elevation. It is called normal lapse rate. At times, the situation is reversed and the normal lapse rate is inverted. It is called inversion of temperature. Inversion is usually of short duration but quite common nonetheless. A long winter night with clear skies and still air is ideal situation for inversion. The heat of the day is radiated off during the night and by early morning hours, the earth is cooler than the air above. Over polar areas, temperature inversion is normal throughout the year. Surface inversion promotes stability in the lower layers of the atmosphere. Smoke and dust particles get collected beneath the inversion layer and spread horizontally to fill the lower strata of the atmosphere. Dense fogs in the mornings are common occurrences, especially during winter season. This inversion commonly lasts for few hours until the sun comes up and begins to warm the earth. The inversion takes place in hills and mountains due to air drainage. Cold air at the hills and mountains produced during night flow under the influence of gravity. being heavy and dense, the cold air acts almost like water and moves down the slope to pile up deeply in the pockets and valley bottoms with warm air above. This is called air drainage. It protects plants from frost damages.